So one of the most important aspects of sediment analysis, whether it's a sediment model or some sort of expedited screening level analysis, is the sediment rating curve. And the sediment rating curve, why we need it and where it comes from, kind of emerges out of the sediment budget. The sediment budget is just a really simple way of talking about the continuity equation in a sediment realm. The continuity equation is really the most fundamental aspect of physics. The idea is that if you have a control volume, you have mass coming in and mass coming out, the difference in that mass either has to be stored or removed from storage. And so, in the sediment budget, basically we've got mass in, we compute all the different places that sediment mass comes in, we compute the sediment mass that goes out, and the difference is either stored or removed from storage. The only difference in sediment transport is that you store or remove sediment from storage on any meaningful engineering timescale by either depositing it or eroding it. And so if the mass in is greater than the mass out, then you're going to get deposition, and if the mass in is less than the mass out, you're going to get erosion. Or really, a better way to think about that is if you erode, the mass out is going to be greater than the mass in. But again, if you integrate it over an engineering time scale, those are the three basic terms. Right, so where did these data come from? We kind of gave you the data in the first exercise, but if you're doing a sediment study, you're going to have to go find these data. And so the storage term is usually the result of repeated bathymetries. You either have LiDAR before and after that you've differenced, or multi-beam before and after that you've differenced, or more likely you have cross-sections, multiple cross-sections, which John talked about, and we have these cross-section analysis tools that you can use to look at what is the mass between the two cross-sections over a significant reach. And so that's how you determine the storage term, the sink or source. Is it eroding or is it depositing? But how about the flux terms? The flux terms are the mass in and the mass out. And while the storage term, essentially we're computing the difference, with the storage term we're essentially computing the difference between two distances. With the flux terms, it's really a concentration integrated over time, or a mass integrated over time. And so you have a mass in and a mass out. But you don't really usually have a mass in or a mass out. We don't usually have continuous sediment time series. What we have actually are flux samples. And usually we don't have a lot of them. And usually a sediment time series, a multi-decadal sediment time series, is represented by a handful of flux samples, and then those aren't even very well distributed. A lot of times what happens, like in this case, is you have some sort of flood event that draws attention to the system, and then you have a lot of flux samples in the 2 or 3 years after that, but then it's pretty sparse elsewhere. You don't always get the peak, or you don't always even get close to the peak, but you do have this handful of flux samples that is what we have to generate this inflow term of your sediment budget or your control volume. And so how do we do that? Well, we do that by building a rating curve. You're going to need a continuous sediment time series coming into your control volume, either for a sediment budget or for a sediment model. And so what we're going to do is we're going to use these data to develop a rating curve, and then we'll use that rating curve to develop the sediment time series. And the way that works is, we only have these discrete snapshots in time of what sediment flux looks like for a few flows, but we do pair that with usually some sort of complete or semi-complete or reconstructible flow time series. And so the way this works out is you have several observations of concentration, and those line up with observations of flow. You plot flow against load, and you have a sediment rating curve. The sediment rating curve often has a lot of spread in it, it often has a lot of uncertainty, but you can generally fit a power function through it and come up with a flow-load relationship. Now that you have a unique relationship between flow and load, you can then pair your rating curve with your flow time series, and for every flow you can pick a load off the time series and develop a full continuous sediment time series that you can then sum up to compute what your average annual or your total flux into your control volume is, or which will essentially be your boundary condition in your sediment model. In your sediment model, a lot of times what you do is instead of bringing in the complete sediment time series, what you do is you just attach the flow series to the upstream boundary condition and then give the model the rating curve, and the model will use those two things to bring in the sediment flux. And so I'm going to show you how to build a sediment rating curve out of some data, and then we're going to talk about a number of considerations that you have to take into account before you build this sediment rating curve. There are a number of things, complexities that you often run into while trying to do this that we kind of need to walk through before you take this on. So the data we're going to deal with are from the Omaha gauge on the Missouri River. You can see that it starts back in 1971. We have over 2,000 observations to present. And the data we have are the date, the time, the flow, and the load. When you download these from the USGS website, it obviously comes with much more stuff. You have to strip it down like this. And then we've also included the concentration. Sometimes the USGS data comes in as load, sometimes as concentration, sometimes both. But you can very easily switch back and forth between these. Concentration is a function of load and flow and vice versa. And really it's just a matter of units conversion. There's this equation which allows you to move between flow and load with a unit conversion coefficient. There's a different one for SI and US customary. I sat down and spent 20 minutes driving this once. You can do that yourself, or you could just use these to move back and forth between concentration and load. Incidentally, sometimes you'll get data in concentration parts per million. And the question is, well, how do you move between that and concentration and load? Well, for almost all alluvial systems, almost any concentration that you will encounter in a river, including like reservoir flushes and even dam removals, the concentration in milligrams per liter and the concentration in parts per million are approximately the same. You can essentially convert them and use them to estimate each other. Now, as you get into hyperconcentrated flows, mud flows, and debris flows, that starts to diverge. And we actually have a calculator in RAS that helps you calculate those differences. Incidentally, RAS 6.0 has non-Newtonian flows, mud flows, and debris flows. And so if you get into those sorts of applications, then it starts to matter. But for almost any alluvial application, concentration in parts per million is essentially equivalent to milligrams per liter, which can be used to compute tons per day. Okay, so now I'm just going to make a rating curve. Now you can make this rating curve out of load or concentration. They're kind of load people and concentration people, just depending on how you think about the world. I tend to be a load person because I think about things in terms of pure mass flux. If you plot this, it's a hot mess. We're going to be hard pressed to see any sort of relationship between flow and load. But one of the things that you'll hear me say a lot is that the defining property of sediment transport is that it's nonlinear, is that load is a nonlinear function of flow. So as flow increases, load increases at a faster rate. And so in order to capture that nonlinearity, we're going to have to plot this in log-log space. And when you plot it in log-log space, now a trend seems to emerge. Now, I had a professor once who said, hey, be careful of anyone who plots anything in log-log space because they're probably trying to hide something. And then I went into sediment transport, where the only way we can kind of make sense of our data is to look at them in log space. So I made a slightly tidier version of this that we can look at. And so here are all the data plotted flow against load. And you can kind of immediately see why we need to plot this in log-log space, is that for a given flow, there's almost an order of magnitude of scatter in the load relationship. Now, that doesn't mean that we can't form a robust relationship out of this, but it does mean that any straight line we use between flow and load is going to have a lot of noise and uncertainty around it. And this is one of the reasons why we tend to do sediment transport analyses on the decadal scale. We tend to do long-term sediment transport analyses rather than event, because a long-term 50-year period of record simulation will integrate a lot of this uncertainty over time, whereas a single event won't be as forgiving. But there are some things we can do to reduce this uncertainty. Some of it's fundamental, but some of it is based on a couple of considerations that we need to screen for. And the first one is stationarity. Stationarity is the assumption that the process has been the same over the time of the observations and will continue to be the same into the future. And this is not always the case with sediment transport. So the first thing I do anytime I get a rating curve is I do a stationarity analysis. And there are quantitative ways to do this, but the most intuitive stationarity analysis is just to plot the early data separately. And so what I've done here is I've plotted all the data from the 70s and the early 80s separately from the rest of the data, and you see that they do tend to cluster on one part of the curve. Now we're going to ask you some questions about this in the exercise, but you'll see that there has been a shift in the load for a given flow over time, and so these data are not stationary. And so if I want to develop a rating curve that I'm going to use into the future, I should probably screen out some of the early data. Another thing that happens is that we are looking at all the data at the same time. But one of the reasons for the spread in these data is that generally sediment load takes a different path on the rising limb of the hydrograph than it does on the falling limb. Now, some of you who are on steady flow models, you're used to looped rating curves in your unsteady flow simulations. That for a given flow on the rising limb of the hydrograph will actually have a different stage on the falling limb. Well, it's similar in sediment transport. What I've done here is under the Hysteresis tab, I've plotted the sequential observations from water year 2011. And what you'll see is that on the rising limb of the hydrograph, which is the up arrow, the arrow to the upper right, the loads are significantly different than the loads on the falling limb of the hydrograph. And again, in the exercise, we'll have some questions for you about that and help you to think that through and develop some hypotheses. But it's worth noting that sediment transport has hysteresis. And so if we're going to represent this with a single rating curve, we're going to kind of integrate the high and the low together and go for an average effect. Okay, but we're going to ignore those things for now. And I'm just going to use all the data because that's what I've asked you to do in the workshop. And we're just going to develop a rating curve. And so the easiest way to develop a rating curve between paired data and Excel is just to right click and ask for a trend line. And what you immediately see is that there are lots of different ways of estimating a trend through scattered data in Excel. And one of the things that students will often do is they'll just start clicking through these and see which one of them looks good. But let's just think about this theoretically before we start clicking buttons. Obviously a linear plot is not going to be appropriate because these data are not, remotely linear. Sediment transport is nonlinear. And so linear is out. But which of these other ones is going to be appropriate? Well, it turns out that sediment transport is usually a power function. Usually load is some relationship of flow to a power between 1.5 and 2.5. Often an opening guess would be that load is some small coefficient times flow squared. And so the power function is going to generally be the way that we try to develop a rating curve. But there's a kind of more elegant mathematical answer there, is that the way we compute a power function is least mean squared analysis, which is just a transformed linear analysis in log space. And without getting into the details of that, although we are going to have to interrogate the details a little bit for the next step, what that means is that when you use a least mean squared fit power function in log space, it plots as a straight line because you're doing a transformed linear regression. And so let's turn on the equation and the r squared to see how bad it is. And if I make that bigger, you can see that our rating curve is in fact load, which is y, with some small coefficient times flow raised essentially to the 1.5. And so it's on the low end of that slope, but it is, consistent with sediment rating curves. So we have a rating curve. But before we charge ahead, there's something you need to know about least mean squared power regressions in log space, and that is they are actually fundamentally biased. The process of transforming and untransforming these data always bias it in the same direction. And so before we actually can use this rating curve, we have to go through an exercise that will unbias the data. Otherwise, our sediment rating curves will always be too low. So before we talk about how to unbias your rating curve, we need to talk a little bit about just kind of basic linear regression. And if you remember, if you're going to try to fit a model, a best fit linear line to some data,
the method we use is what we call least mean squared. If you just right-click on some data in Excel and ask for a linear regression, they're going to do a least mean squared analysis. And basically, all that does is it calculates the residual, the error between your model, which is your line, and each of your data points, and then it tries to fit the line that reduces the error, that essentially minimizes the square of the residuals. And so if you do this with a power function, here's a power function. I know that because I created this power function myself and then introduced some random scatter around the function. If we're going to fit a line, fit a power function model essentially to these data, it turns out to be relatively straightforward, because when you transform a power function into log space, it turns out to be linear, right? So the log of the dependent variable equals the log of the coefficient, which becomes its own coefficient because that's a constant, times b, the power becomes the slope, times the log of the independent variable. And so you just get a straight line fit, and we do the exact same least mean squared error analysis in order to get the best fit line. And so that's super easy, except that when you untransform these data, you end up with a systematic bias. Let me show you how that works. So if you are minimizing residuals in log space, okay, here we have two residuals in log space. The log of the load here is 0.7 and the log of the load here is 0.7. And so these residuals would offset in a least mean squared error analysis. But then you use that to find your power function. If you were to replug these data in to the power function, the actual load on the low end is going to be 8,000, where the actual load on the high end is going to be 16,000. The high end residuals end up being higher when you untransform the analysis. Okay, that's super complicated, and I understand that maybe you clicked on a video where you wanted to learn about sediment rating curves, not log transform residuals. But what you need to know, the takeaway from that, is that if you fit a power function to log data, it's going to be systemically low. You're going to have a bias in that so that your rating curve generally produces too little load for the flows that you select. And it can be to the tune of 30 to 40%. And so what we need to do is we need to do some math to unbias our rating curve. And there's a number of ways to do this. There's several functions. None of them are elegant. The one that the USGS uses and the US Bureau uses and that we've kind of adopted as core SMEs is what we call the Duan smearing factor. It comes from Duan 1983. And yeah, that's how precise this is. We call this the smearing factor. But the idea here is that we're just going to put a new linear coefficient in our power function. And this linear coefficient is going to back out the residuals and compute what the bias would be approximately based on the residuals. And so in this case, we've computed what we call this Duan factor of 1.32. What that means is that the correct rating curve, the rating curve that actually will reproduce the right loads, is 32% higher than the biased rating curve that you would get from a least mean squared regression. Now, how do you do this math? You need to work up a spreadsheet. That's really complicated. The math isn't complicated. It's easy to make errors. I've included a link to the spreadsheet in the description of this video. And my spreadsheet was actually built off of a spreadsheet developed by Dr. Blair Greiman from the US Bureau of Reclamation. Let's share spreadsheets. And so you'll do that in the workshop. All right, so let's talk about where we've been. You've developed a rating curve, but you can't just right click on your data in Excel and fit a power function to it. There are a number of ways you just have to think about these data before you can just do some simple math. And so we talked about analyzing your data for stationarity, thinking about how hysteresis affects your data, and then applying this bias correction. But there are actually several other ways that it's appropriate to think about the data and adjust your rating curve. We deal with them in more detail in the HCRAS Sediment Manual, but let's just talk about two more. The next one that we're going to talk about is supply limitation, or what we'll call an inflected rating curve. So these are data developed by Dr. John Shelley, who's the other instructor in this class. And what Dr. Shelley did is he did a study of all all of the sediment data in the Kansas River Basin. And one of the things he found was that when you develop your rating curves for the rivers in the system, you'll find that there's one line for the lower to moderate flows, but higher flows have a different trend, and it tends to be a lower slope trend. And he saw this on all of his systems. And when he went in and looked at, well, what flow does that inflection point happen at, it actually turned out to scale to most systems, that it turned out to be about the 1.2 to 1.5 year event. And so that turns out to be close to bankful flow. And so you can do your own thought experiment about why would this be inflected at bankful flow. But to kind of get away from the dynamics of this system, this is very common. It's very common for high flows to actually have a different flow-load relationship. And we call that supply limitation. A system is supply limited when, as the flow increases, the sediment transport increases more. It's nonlinear. But at some point, you get to a flow where the river says, hey, I can move lots more sediment, but the supply says, hey, I don't have more sediment to give you. And so even though the river could transport more sediment, it's supply limited. It's limited by what can be supplied to the river. And so you end up with a flattening curve. Sometimes called this a flattening curve, a inflected curve. But if you were to just fit even an unbiased rating curve through these data, you would way overestimate the transport at your moderate to high flows, even your channel forming discharge. And so you would way overestimate your sediment flux. And so you just have to actually think about this and look at your data and think about how your system works before just fitting a rating curve to your data. Right, and then the final thing that you want to think about when you're developing a rating curve from flow-load data is what we're going to call serialized correlation. The USGS has done the most work in this. If you go to the USGS statistical manual, they have a whole chapter on this, and they actually have a program that they've developed to help you compute this. But I'm just going to kind of introduce it qualitatively. And so these are actual flow load data that I got for one study. And when I first plotted them, just flow versus load, I thought, oh, I have a decent amount of data here. I can develop a rating curve. But something made me suspicious. The thing that made me suspicious about these data is that a lot of them were just lined up. And these vertical lines in your sediment data should tip you off that maybe something's not entirely right here. Because what does that mean? Well, that means that you have multiple loads for the exact same flow. And what are the chances that they went out on lots of different days under different conditions and just happened to have the exact same flow? Yeah, not high. And so if you plot these based on the day that they were taken, you'll see that all of these data were basically taken on 1, 2, 3, 4, 5, 6 different days. And actually, the vast majority of data were collected over a 3-day period. Now, this is not uncommon because a lot of these gauges, they don't have long-term budgets for sediment data. Basically, after a flood or after some sort of public meeting, there's a little bit of funding to go out and get some data. And so the data tend to be temporally clustered. But should we just regress these data? One of the assumptions of linear regression is independence. Are these data independent? They're not. And so you need to make a decision if you want to collapse these data into an average for that event, or if you want to use them independently. And as I said, the USGS has developed software to help you make that decision, but you could also kind of make that decision qualitatively and say, hey, are these data independent? And so this is another case. This is on the Mississippi, and our Mississippi data are actually often like this. You'll see that the gray dots, those are samples taken before 1984. And you'll actually see some non-stationarity in this plot. But the brown dots, those are samples taken after 2010. And you'll notice that the samples taken after 2010 have that vertical striation. And that's because after 2010, they decided, hey, we shouldn't just go out there and take one sample. We should go out there and take 12 samples. We've got the boat out there. It takes way more time and effort to get the boat out there than it does to take samples. So let's take a bunch so that we see the scatter. And you'll see there's actually a lot of scatter. But if you were to regress all these data together, what would it do? Well, it would overrepresent the data for which there were more samples. It would treat each of these later samples, each of these replicates, as an independent sample and give it the same weight as the historical samples, which actually are independent. And so in this case, it would be appropriate to do some sort of averaging with the newer samples in order to not overweight it with the older samples. But this isn't always the case. And so this is the Rio de la Plata data. This is the flow load curve from the Rio de la Plata. And again, you see I did a little stationarity analysis. And you'll see that most of the data in the higher flows, which is really what's going to drive this rating curve, were actually taken over only like 3 sampling days. And so should I just average them into single data points? Well, if you look at the October 7th data, all of these samples were taken on the same day. But if you take 12 samples over a day on the Mississippi, the flow is functionally the same. The Mississippi doesn't rise and fall in a day. But the Rio de la Plata will go through a whole flood cycle in about 36 hours. And so even though these are all taken on the same day, they vary from like 8,000 to 40,000 CFS, which means that even though they're not temporally independent, for our purposes, they are relatively unique analyses of how a particular flow is related to sediment transport. And so for the Rio de la Plata analyses, I kept these because they are snapshots of independent events, which is the sort of thing that the USGS guidance on this recommends, is you look at the change of flow between these temporally clustered data points and make a decision about whether or not they're independent. Okay, we'll end there. There are other considerations, but you get the idea, is that you're going to develop a rating curve from your flow load data, but you need to actually think about it a little bit. You can't just right-click and get your power function. We're going to go through some of these in the workshop, but one of the things that we've done is we have started to develop a rating curve analysis tool that does each of these for you. It's a pretty cool tool. We have proposals in to continue to develop it, but that's kind of where we're going. We're going to try to provide you resources to do this in a systematic way, but for now, we will work on this in the workshop.